Hi everyone, welcome to the latest in our series of EuCAPT video profiles where we interview leading members of the astroparticle and cosmology theory community, try and find out a little bit more about what they work on, but also a little bit more about what makes them tick as people. It's a very great pleasure to have Valerie Domcke here with us, who is a staff member at CERN. Welcome, Valerie.
Thanks, Bradley. Nice to be
Um,
here.
So I could probably give a very long introduction and say a lot of things about you, but maybe it's better if I let you do that. So why don't we start off at the very beginning? Why don't you tell us a little bit about how you became interested in physics?
Well, I guess it started as a kid. So kind of the books that I enjoyed reading was science fiction. So all about exploring the universe. So a bit sometimes I have to smile when I think that that's what I'm actually doing now. Not that far away. Um, and yeah, I mean then kind of at schools, science was what I enjoyed. And so that kind of put me on that track.
Yeah, you go from thinking about exploring the universe to actually learning the details of what the universe looks like.
Right. Though I actually have to admit that I stopped doing physics 2 years before my final year because there was a limit to two science subjects that you could take, and math and chemistry just had the more fun teachers.
Okay, but it wasn't the subject matter, it was the teachers.
It was the teachers, yes.
Okay, so what brought you back to physics?
Well, I did a kind of a little test. I mean, like you could, as a high school student, you could go to university and kind of try out how it is to be a student.
Yeah.
So I did that for math for 2 weeks, and it was horrible. I mean, it was all this axiomatic. I enjoyed solving puzzles, right? And here was all this kind of axiomatic, ginormous overhead.
Okay.
It was just not for me.
It was more contact with kind of real problems or real puzzles that you felt like you could sink your teeth into.
Yes, yes. I wanted a puzzle. I wanted kind of something that I felt, okay, if I understand that, I actually understand something.
Okay, okay.
True, really about anything, right?
Yeah, the
Um,
maths was maybe a little too abstract and axiomatic.
right. Well, yeah, at least kind of the way it was presented in these 2 weeks, right?
Yeah.
And so then I was out, and then chemistry, I just spent too much time in high school on a project where I had to um, identify different like natural pH indicators. So I spent a ton of time collecting various plants and taking pictures of how they reacted when I put lemon juice and washing up liquid to them. And I
Okay.
was traumatized. Um, and so physics it was.
It's, I guess if the alternative is exploring the universe, it was not that big a choice to make between putting lemon on plants and trying to understand the universe. Okay, so maybe you could tell us a little bit about your career trajectory. So once you came back to physics, where have you been since then?
Yeah, so I did my undergraduate studies in Munich, including my master thesis at the Max Planck Institute. And then I moved to Hamburg for my PhD, then to Trieste in Italy to first postdoc, to Paris, as you know well, right, for a second postdoc, because that's where we met. Then back to Daisy as a junior faculty, and then finally down here to the Geneva region, first on a combined position between CERN and EPFL, and now I'm fully at CERN.
Okay, nice. It's quite a lot of exploring.
Yes.
Not quite the whole universe, but certainly exploring a few different places. Um, okay, so maybe you could tell us a little bit about what you work on, or maybe more broadly, what are the questions that you're trying to answer in your research?
Yeah, so I work on the interface of particle physics and cosmology. So I'm interested in what different cosmological or astrophysical observations can teach us about the open questions in particle physics. So that can contain a range of things that can contain on more particle physics side, kind of model building to solve open problems in particle physics and then see if there's any cosmological implications of that, or kind of studying various signatures from the early universe and then thinking about how any modifications of the standard model of particle physics would impact them. So most recently, I've been working a lot on gravitational waves.
Yeah.
Gravitational waves across all frequency ranges. So in the CMB, but then also now pulsar timing arrays. I mean, very exciting now that we have a first signal.
Yeah.
Then, I mean, we have instruments coming up in the next decade, such as LISA, hopefully the Einstein telescope. LIGO is just pouring in data. And then I'm also kind of looking at then possibilities to go to even higher frequencies to see if we can. That's kind of a field that is still very much in its infancy, and kind of just thinking about what sort of a detector concept would you need to even attempt a detection.
Yeah, this is very high frequency, right?
Right, that's above LIGO, so that's kind of up to, well, in principle, from kilohertz to gamma ray frequencies, right? X-ray frequencies. Though the higher you go, the harder it gets. Okay. So I'd be already very happy if we can get to the, say, megahertz range.
Okay. The discovery of gravitational, or the observation of gravitational waves directly, was a pretty exciting point. What did that kind of change the way that your research was going, or were you already thinking about gravitational waves?
I was already working on gravitational waves then, basically because it was something my supervisor suggested me to do, which meant that I kind of suddenly became an expert, right? Because I had 2 papers. Now everybody has 2 papers on gravitational waves, right? You're not an expert with that anymore.
I do, of course.
Yeah, so that I mean, that definitely, it boosted the field enormously. Though at the time, I don't think kind of I realized quite how big of a thing it was, because I mean that was kind of just after my PhD, and I just thought it was kind of normal that there's kind of a major discovery every other year, right? It took me a while to realize that no, yeah, that was actually big.
Yeah, this is a huge event. And then, so you're looking forward perhaps to other detectors coming online, like you mentioned LISA and Einstein telescope.
Yeah. So I mean, in particular, I think LISA is going to be very exciting just because it's a frequency range where we basically have no probes at the moment. So we go from having essentially nothing to having an incredibly sensitive instrument, which is going to be amazing. It's also going to be extremely challenging. Like I make the comparison that it's a bit like going from some Rutherford scattering experiment to turning on the LHC with nothing in between. Right. Okay. And the thing is in space, right? So you can't go twiddle with anything.
Yeah, it has to work.
It has to work
from the get-go.
You have to understand the instrument. You have to kind of understand how to do the data analysis. So there's going to be very, very exciting times.
Okay. And so what kind of things are you hoping might be discovered with LISA? What are the new things that you would be looking for?
So I mean, it's probing a temperature range in the universe around the electron-weak phase transition. Okay. So that's kind of a very promising range, since there's clearly things about the electron-weak phase transition and things about the Higgs that we don't understand. So having another instrument looking at that epoch from a very different point of view is, I think, going to be interesting.
Yeah.
But then there's also like a range of other things like say topological defects, primordial black holes. I mean, there's a lot of models that are very well motivated from other aspects, but that were not kind of built with the target of generating a signal at that frequency, but which actually address open questions in particle physics.
Yeah.
So in that sense, we learned something important. Even from a I mean, it won't be a non-detection, because I mean, if we don't see anything, we've done something wrong, right? Because there's going to be a ton of astrophysical signals, which in turn can be precision probes of particle physics. But if we don't see any clear signal from the early universe, like if we don't see a stochastic background, we'll still have learned something, because we'll be putting kind of constraints on very relevant regions of parameter space of very relevant models.
Yeah. Okay. So this is the idea that you can look for the gravitational waves which are produced in the very early universe
Right.
through phase transitions and things like that.
Right. I
Okay.
mean, take for example, I mean, cosmic strings, right, which are formed if you have some U1 breaking in the early universe, which could be related to some gut scale unification.
Yeah.
I mean, Lisa will kind of bring just the scale of that measurement down from the gut scale really down a few orders of magnitude. So if we don't see anything, it means that, with some small caveats, right? It basically means that there's no U1 phase transition or no phase transition that gives us cosmic strings
Yeah.
at high temperatures in the universe. So we're actually probing particle physics from above
Okay.
instead of probing it from below, as what we always do in colliders.
Yeah. It's incredible that we might actually be able to probe and say anything about that period of the universe. I mean, it's not a technologically simple task, and it's certainly not a from a data analysis perspective. Like you said, it's like turning on the LHC when all you've ever known is Rutherford scattering. But still, it's incredible that you might be able to learn so much. Are there any big obstacles in the field of uh, astroparticle physics right now?
We're in a nice situation that we have a lot of data coming in, which is very nice.
Yeah,
I think what makes it maybe a bit difficult at the moment is that we don't know exactly where to look. Like more on the particle physics side that has kind of been guiding us on where to look.
hmm.
I think it's less clear on what is the target. I mean, it's less clear what is the dogmatic candidate we should be looking for. What kind of what is the resolution of the hierarchy problem, and the fact that
Yeah,
we kind of don't have clear answers from the particle physics side means we need to look at kind of all sorts of astrophysical systems, and just try and understand very complicated environments in the hope to kind of get a glimpse of what might be going wrong. I don't think it's really an external obstacle, right? Unless you want to count that just nature is being difficult. But I think it's more that as a researcher in this field, nobody can tell you, okay, this is where you need to look, right? But people need to look a bit everywhere, and they need knowledge of a very wide range of systems, right? Also to make sure that something you're constraining in this particular system is not actually constrained from something completely different.
yeah, yeah.
So
Okay.
I think that makes it fun, right? Because it means you learn lots of new stuff all the time. A lot of variety in what you work on. But of course, it also makes it a bit difficult, and it makes it kind of impossible to kind of have I think, a very clear plan saying, okay, here's the next 30 years, this is what the field has to do.
Yeah,
Depends a lot what we find on the way.
yeah. A lot of people don't just work on one very specific thing because there isn't necessarily the very concrete direction or motivation to just focus on one thing because, like you said, there are so many different avenues and possibilities. Yeah. I think you also mentioned this idea of it depends very much on what happens along the way or what we find along the way. And one of the themes that people bring up sometimes when I talk to people in this context is this idea that you start some new experiment, you build a telescope, whatever, and once you open the box and start looking at the data, you really have no idea what you're going to find. And like with gravitational waves, we really had no idea what the population of black hole binaries was in the universe until you open up the box and discover that it doesn't look quite like what you thought it was going to look like. And
Yeah.
so everything just becomes very broad very quickly.
Yeah. Also, I mean, for example, neutron stars, right? I mean, we knew neutron stars were interesting systems, right? But when I saw just the wealth of information that came out of one single neutron star merger, right? But then we've also only seen one such clear merger to date, right? So we're also very lucky that we had such a nice signal so early on.
Yeah.
So there's a lot of also luck in what we see when we turn on the detector.
And so maybe if we project forward even further, like in the next 50 years or so, what do you think we might be able to achieve in astroparticle physics, astroparticle cosmology?
I kind of just told you, right, that that's a hard question to
Yeah,
answer.
yeah. This is
But that that said, I mean, I think if in 50 years we still don't know what dark matter is, I'm going to be quite depressed. Because I feel like that I mean, we should figure that out on a timescale that is much shorter than that. And I would sure also hope that we've maybe resolved the Hubble tension by then, one way or the other. I hope we manage that a lot earlier than in 50
Yeah,
years.
let's hope that nature isn't being too difficult and we manage some of these things on shorter timescales than 50 years.
Right. I mean, it's a bit. I mean, if one looks back, I mean, there's been periods where everybody was kind of super focused because they knew a bit what was the next thing to do. Which, okay, maybe also in hindsight it looks like that, right? Right? Maybe at the time it was not so clear, right? But if you look back, there was kind of clear periods in time where the standard model was developed, where supersymmetry was developed, where everybody thought they knew where they were going. Yeah. Now we are, I think, in a period where we're more going broad, right? We're exploring different options. I would expect we will enter again a period where we kind of think we know where we're going.
Okay.
Then we'll see if that was actually the right direction.
Okay. So maybe we can change direction a little bit and think about not so much your research, but being a scientist in general. What is it that you like about being a scientist?
Well, I like nearly everything about being a scientist. So, I mean, I like the incredible freedom that we have. I mean, basically all the time I can work on whatever I think is important, right? I mean, I did be a physics question that I think is important, right? Or some more kind of organizational thing, but again, I do it because I think it's important, right? Yeah. I mean, like here, I mean, we do this interview, right? Not because some big boss has told us that we should be doing it, right? But because we think it's a good thing to do.
Yeah.
And that I think is incredibly valuable, right? I mean, I nearly never have to do something just because somebody tells me to do it. And then, I mean, I enjoy meeting new people, kind of facing new problems every day, learning something new every day. Getting to see new places.
Yeah.
And just meeting young people. Well, I still feel I'm still kind of young, but meeting even younger people, with new ideas and kind of watching them grow and watching them develop their ideas. That's fun.
It is a lot of fun. So that's a very positive view of being a scientist, which I share. But there must be some downsides.
I actually, okay. I mean, I think there are difficulties, of course, right? I mean, it is a very competitive environment. There is, I think people do feel or can feel a lot of pressure to work too long, to not take care of themselves enough.
Yeah.
There is the kind of the difficulty that there's basically the external pressure to move every couple of years, which personally I enjoyed it, right? But I can see that there can be circumstances where that's not fun at all, right?
Yeah.
So I think kind of finding a balance between and doing good physics, but also kind of taking care of yourself.
Yeah.
Is something which, okay, I mean, not only in physics but in society in general, right, is not always valued enough.
Yeah.
And we're definitely not an exception, right? I mean, we definitely have all these difficulties. I do see that things are improving. People are kind of getting more conscious and are paying a bit more attention. It's still far from perfect.
Yeah. It's good that it's improving, but yeah, finding that balance can be difficult, especially when it does come with so much freedom.
Yes.
I mean, those two things are very difficult to manage. So what do you like to do if you do find that you've worked some long hours? What do you like to do to unwind and relax?
So my favorite way of relaxing is to go sailing.
Okay.
So we have a nice big lake here. And this is a hobby I picked up, as I was moving around and looking for new people to do new stuff with, right? Then I ended up in a sailing club. And yeah, that is for me just the way to once I get on the water, my brain just disconnects from physics. I can be on my way there and I'm still thinking of things I need to do and things that I will do after sailing, blah blah blah. Then I get on the water and just the brain is erased, right? And it's just sailing in me until I get back to the office the next day. So,
But that's fantastic. I think a lot of people are looking for that kind of thing. Really struggle to find that kind of disconnection.
yes, I recommend sailing. I recommend the occasional capsize. I promise you, you're not trying to solve problems anymore, apart from the problem of how do I get back onto my boat.
Okay, that puts things in perspective.
Yes.
Okay, so very well about EuCAPT and the role that it plays. The idea is to kind of stimulate communication and collaboration, bring together institutes working on astroparticle theory and cosmology across Europe, kind of develop a collective force and a collective voice for those groups. Yeah, how do you see EuCAPT's role? Or maybe I can ask a more specific question, which is, you've worked quite a bit organizing the EuCAPT symposia. Do you see that those events are kind of bringing people together?
Yeah, I mean, what I like a lot about the symposia is kind of how many people come, and how many young people come.
Yeah,
And it just shows how big the field is, and how many people work in this field that I hadn't met before. And so I think a big, and in particular because astroparticle is kind of such a broad field, but also you cannot just hide in your niche, right? You kind of need an overview of what's going on. You don't need to be an expert in everything, but you need already at a very early career stage, you need an overview of kind of a bit globally what's going on, because otherwise you kind of risk going down a rabbit hole that in the end you constrain some parameter space that is just zero because it's long excluded by other things.
yeah. As you were saying earlier, every plot basically has a whole bunch of lines on it coming from very different places, and you need to make sure that you're actually still looking at an interesting bit of parameter space.
Right,
Yeah.
right. So I think and that I think makes it very important to kind of connect the community, because not everybody can be an expert in everything, and not every group or every university can have in-house even the expertise to kind of extract from the archive or so all this information.
Yeah.
And so kind of connecting, so I mean hearing of course the talks, right, but also then knowing, okay, here's a person I can ask if I have a question about this.
Yeah.
I think that is very important, and I think that is maybe the key thing that EuCAPT
Yeah.
can do. But then of course it's also about kind of a bit coordinating a voice, precisely because the community is so diverse, right? To kind of, okay, if we have a scientific consensus that there's one experiment that we really want, or there's something is more important than the other, something that requires big funding, right? Then
Yeah.
of course having a unified voice can be very useful.
Yeah, it really helps. Yeah. Especially the this building of networks is very, very useful. But as you were saying, in general, with physics, finding the balance between the work and the productivity is tricky. And I know that organizing these things has been a lot of work for you and the other people involved. But I know you've been spearheading it a lot. So thank you for that.
Well, you'll find that I give different answers depending on if I'm in the process of organizing it, right? Or then when the event is happening, right? When the event is happening or has just happened, right? I'm very happy because it's a lot of fun.
Yeah.
Um,
Okay.
when you're dealing with people rather than with emails, it's all is compensated.
But that's good. It reminds you of the reason that you were doing all the organizing in the first place. Yeah. Okay, so maybe my last question can be, what advice would you give either to your younger self, having just left chemistry and maths behind and come back to physics, or to a younger colleague just starting out in the field? What piece of advice, either in terms of which direction their research should take, or how they should approach research in general?
I think I would say that you should do what you're interested in, and you should not strategize too much, and you should not listen to senior colleagues too much. So
Yeah.
so I think because you're going to face difficulties, right? You're going to face kind of problems which are difficult to solve. You're going to face minor science which take 3 months to find, right? So there's going to be some frustration along the way. And if you're doing something because somebody told you to do it, or because somebody told you that that's the best way to get a job, that's very difficult to pull through. But if you're doing it because you think this is interesting, I think you get further, you do better research, you write better papers, and you have more fun.
Yeah, you
right?
personally can get more out of it that way.
Yes.
Yeah.
Yes, and I think when you're doing that and when you're having fun and you're getting more out of it is also when you just do the better research.
Yeah.
And very important, what I would recommend to be, I mean, when one chooses a supervisor, chooses a PhD project, right? I mean, it's a commitment for whatever 3-4 years, depending on the place, right? So,
Yeah.
so I was super lucky. I had absolutely amazing supervisors. But I would kind of be sure that this is a person you want to work with, right? People can
Yeah.
be amazing scientists and bad supervisors. So kind of say find a former PhD student, talk to them,
Speak
and
to
make sure this
people.
is the type of person you want to. I mean, some people work well with. I mean, some people just work well together and others don't, right? They just have different styles of working.
Yeah. Yeah.
So somebody can be a good supervisor for somebody and a bad supervisor for somebody else. So just kind of hearing about what is that style of supervision, if that works for you, before committing 4 years of your life.
Yeah. It's a big commitment.
Yes,
Yeah.
very important.
Okay. So I think maybe we can stop there. So I'd like to thank everyone for listening. I want to thank Valerie for taking the time to talk and for considering that the interview was important or meaningful enough to do. That's why we're here doing it. And let's hope that nature is not too stubborn and difficult, and maybe we'll make more progress in the next 50 years than we imagine. So thank you very much, Valerie.
Thank you.
Thank you.